Hello and welcome to another Solana hacker challenge with a Solana tutorial. Today we're gonna talk about disassembling Solana programs. Yep, that's what we're gonna do. Cause some of you really enjoyed the Pinocchio hacker challenge and you told me you want more of these kinds of challenges. So here I am, providing you with another challenge. So first I'm going to give you the challenge and then I'm going to give you a tutorial on how to disassemble Solana programs, which might or might not be related. I have hair standing up here and that's okay. So let's just get started writing a quick Solana program with Pinocchio, because we like that. Disassemble, cargo init, cargo add Pinocchio, make it a lib. You know all this, I'm going to speed run through this. We're gonna do no standard and I will want the lazy entry point. Oh, use the lazy program entry point. Then we're gonna change this to, for me it's the pointer to, the first account, which is the input to the program. But yeah, I can also call it context. We're gonna do something super simple. We're just gonna read a number from instruction data. So from the context, should I read it unchecked? Let's do it this way, which is a slice of U8s. Perfect. Input number a U32, for instance, from little endian. Instruction data 0 to 4 bytes are in a U32. Yeah. Unwrap or 0. Oh, what if I say or default? That will default to something. Okay, I hope this defaults to a 4-byte U8 array. This is what I would expect it to default to. I can say or and then write that explicitly, but I will just, no. So then we have the input number or 0. Okay, and now comes the fun part. I'm gonna do a if my input number equals a magic number, let's say 64, that's too small, something. Then I can't do a formatted message, but I can do a message. Oh no, I got hacked. You made it. So that's where you want to get to. And then I return okay. And otherwise, you can't hack me. Simple program. Super simple program. And that's gonna be the entire program. I don't want no allocator. That's the program. And I will deploy this. In fact, let's deploy it right away. NDS. Nice. For Pinocchio. I like it. So first we gotta build it. Easy. Then we gotta deploy it. hackme.so. 7 transactions. Gets deployed to hackme. Then have fun. So that program is deployed now. You find it on devnet. And your task will be to get there. Just, have it print that. Then you won. And I'm gonna change it a little bit because otherwise you're just gonna be like, well, I saw the source code. Here's the number. That's gonna be too easy. And I'm gonna give it a challenge also in separate increments of difficulty. So I'm gonna work on this version, but then you get to work on a slightly modified version, just so it's not the exact same and you actually have a challenge. And your task is call a transaction that prints you this message with this program. Now, the easiest way how you can do that is obviously to look on chain what other people did so far, but that's a bit boring, honestly. Unless you've never done that before, it's a good skill to have, to look on chain and see what has happened so far on this program and find the right input to then also print that message. So go ahead and do that if you've never done that. But I'm assuming that most of you know how that's done and you wouldn't really learn much by doing that. So I encourage you not to look on chain and really try a different strategy. You could, for instance, try to fuzz it. We talked about fuzzing in a previous video. That could work. Or you try the approach of this video's topic, which is to disassemble it and see what you can learn from that. And honestly, I have no idea if it's possible. Well, I'm pretty sure it is possible, but how complicated it is to read the disassembled code and try and guess that number. So that's what we're gonna do now. We are actually gonna disassemble it. But as I said, this challenge comes in different parts of difficulty. The highest difficulty is you start now without watching the rest of this video and just see if you can manage yourself. But if you're completely lost and you have no idea, obviously, you can watch me go through it and see what I learn trying to hack my own program and then go from there. So you know what's best for you. You make that choice. So I'm gonna go and try and disassemble this program now, pretending that I do not know the source code. All I know is this program ID, and that's it. That's all I know. So the first thing I will need is the executable that I find on this account. And I can either come here and download it, or I can do that on command line. I think it's Solana program dump. And then I give you the program ID. It needs an output path. Okay, you can have that. Dump.so. Write program to dump.so. And then I can hex dump this dump. And I get the program. That's the bytes that are there. Those things. Looks like a program, I guess. And just to compare, I can hex dump my target deploy hackme.so, and we will see that that's the exact same thing. So obviously I could have worked on the SO file directly, but you can't because you don't have the source code and you can't build it, but you can get the dump from on-chain. And that's just, you know, the binary. I mean, this is really hard to read. Like from here, trying to find the correct number, that only works if you know it. But we don't. We totally don't. So, yeah. So, let's see what we can do. Let's see how we can disassemble this to at least get the assembly code. LLVM object dump. Yeah, I think that's what I want to use. Object dump. Gotta install that. Okay. Yeah, I have that. Cool. What does that need? Pass file as argument to read options. Object dump, options, input object. If I just do this with my dump, I guess it needs options. Display all available header information. That sounds nice. I want that. Demangle symbol names. What does that mean? Converting a compiler mangled name back to human readable name. Yeah, if we can do that, let's demangle. Disassemble all executable sections found in the input files. Sounds also good. This is just executable sections, and this is all sections. Okay, maybe start with executable sections. Okay, let's just try some options. Let's just do disassemble executables. Demangle we said we want. Header information, why not? Let's try that. Oh look! We get something. So we get line numbers, we get the hex code. Oh, look at that! Entry point! It demangled that. Wait, is that demangling? Hold on, if I don't do demangling. No, there is also entry point. We have sections. Text, that's the static program. So that's, you know, this part I think is in text. And here we basically see the sections of this file, I guess. Where is what? So we have 0 at 0 and text starts here. Byte 120 with size 1200. Oh no, that's hex. 4600 bytes, I guess. So yeah, there, that's the beginning. Starts the entry point, I guess. And then each of those has 8 bytes. And how many lines do we have? 8 times 6, just roughly. 8 times 6, 11 is, haha, yeah, that's more. We also don't start at 0, start at 36. So that's that times 8. Yeah, that's just short under the 1, 2. It's efficiently packed here, the text. That's almost the 11F is almost the 1, 2, which is the size of the text, so the program. So we know this part is actually what we disassembled here. After the program comes the data, and first is the raw data, which is read only. I learned that in Jonas's video. And I just have 152 bytes of read only data. Probably those are the strings. And then there's more data for rel read only. I don't know. Then we have other sections. So that's always the size, and that's the basically where it starts. This plus this is this. Plus this is this, and there might still be padding. So, dynamic sections, we've got flags. I'm not really, like, it's cool to see this, but I don't have, like, much that I can do with this information. So, that's the decoded header, which is probably in here. I've got an ELF64 BPF format, and that's the start address. Nice, that's where it got this from. Cool. I mean, so far so good. Before we dive into actually looking at the disassembled code here, I want to see what happens if I tell it to disassemble all. So now it also disassembles the other sections, and let's see what we can find here. I don't want to go too deep. Like, I could research what all of those sections are. Just want to look through the sections. Maybe I see something interesting somewhere. I was hoping I can find the strings somewhere. Raw data. Read-only data. I mean, what would I expect? Let's peek in the source again. I have two L's. What if I have congratulations and then a hex dump? There we have the 6C, 6C. That's the double L, I think. I'm gonna find a 6C in here. Yeah, look at that. Here it is. That's my string. The 470. Yeah, but switched, because this is little endian. This is not. So we have 7475, 7261 instead of, you know, the other way. But still, we have two 6Cs after each other. So what it's doing here, it's trying to disassemble the raw data, which doesn't make any sense now realizing that. So disassembling all is maybe a bit pointless, because those things might not actually be code. I mean, this might be, but this here doesn't make really sense. This doesn't make any sense. This stuff doesn't really make sense. And neither does this stuff, because that's actually our string that we have here, but it's trying to decode it as, you know, executable, which it isn't. It's just read-only data. So there must be a better way to decode this. Tell me again what you can do. I'm looking for something with strings. Or is there a separate? I have strings. Display printable strings in files. I mean, I can't just look for strings in files. And look, supported target ELF64. I don't see the one that we have, but let's just try. It's not going to be too different. Scan the entire file, not just the data section. Oh wow, otherwise it scans the data section. Only scan the data section of the file. Yeah, the data section, you know, this part. So the raw data and the data rel raw. Okay, let's try. Strings for this dump. Oh wow. Okay, so I find strings. I find lib.rs. Probably the panic handler can panic in librs and therefore saves this as a string to print where it died. Oh no, I got hacked. Congratulations, you made it as a string. You can't hack me as a string. And then entry point, sol log, sol panic are strings. And those are also strings that it finds, but they are probably, say, where the raw data is, something like that. So that's probably part of the ELF. But yeah, we find our strings. We just don't know why. Like I would like them. I saw that somewhere. Hold on, where did I see this? Let's go to Jonas's video. CU optimizations. Here in the counter ASM or in the counter C. He also does the object dump. What does he use? Print IMM hex. Full leading address. Debug vars. Section headers. Source. Disassemble. Oh, and then he writes it to a file. If you wonder where the strings that you're printing are actually saved, find all strings. Yeah, but I mean that, okay, yeah. He also just does strings. And directly print the raw data section using object dump. Oh, -s, maybe that's something with, ooh. We're gonna do that. What's S? Full contents. Sure. And what's J? Oh, just a section. Okay, I get it. So if I say SJ of my dump, so I just want the raw data. Then it prints that part only. So that's the literal bytes of the raw data. And here we have it in hex, and here we have it in ASCII. Out of range for slice length. That's a string. So that error can happen, and that's why it saves that error message as a static string, as a read-only string. So yeah, apparently those errors can still happen somehow, and that's why we need the error messages for it. But yeah, I got the source librs. I got my two strings, number 1, number 2, and then a bunch of other stuff. Now, we will not find our magic number in here. Why not? Well, because the magic number is just a 4-byte number. You wouldn't put that in the read-only data because that's small enough to take it as the what is it called? When we did the assembly video, we talked about that. You know, that kind of the value part of the instruction. You always have like a move into this register from this part in the memory, or this exact value, and then we just use this exact value, so it's just gonna be somewhere in the text area, so in the program instructions, not in the raw data. We will not find our magic number in here, but it's good to know where those strings live, because maybe that will help us if we then actually look at the assembly. So let's actually look at the assembly. Let's do like Jonas did here. Symbolize operands source. Yeah, I think I'm just gonna do this exact same thing and see what happens. From my dump, then I get this. Oh, then I always get this part. So it now tells me where it's jumping. And now when we do that, please write it to disassemble.so. So now we can look at this as a file. That reminds me of the time when we actually, you know, wrote assembly. We also just used text. Let's see if we can read something interesting from here. Because I mean, it's 600 instructions. I probably don't want to go through all of them, but I don't think I need to, because this program can't be so difficult. And in fact, I already see it. It's like into my face, but only because I know it already. It's not so obvious if you don't know it. So let's see what's happening here. We write something into R2, the R1. R1, by the way, is the pointer to the whole input data. So R1 points to where the accounts live. So the first thing here is, I think, how many accounts there are. No, what's the, I knew that. Here in the FAQ. I know that I always find it in the FAQ. 8 bytes unsigned number of accounts. Yeah, that's what I'm saying. So we get the number of accounts. That's the first 8 bytes. So the first U64 pointer at R1 plus 0. So where R1 points, here it's reading into R2 the number of accounts. Then if number of accounts is not 0, go somewhere else. So that's entry point plus A8, 0x11. So it would go, I don't know, somewhere. So that's 17 and we're at 40. 40 plus 17 is 57, which makes sense. It would then jump here. That makes perfect sense. Look at that. Because here is an exit. So that's likely that from here, it will never go to here. Like from line 57 or instruction 57, whatever, it will never go to instruction 58 because that's always exit. So it makes sense that you only get here from a jump, so from a go to. And in this case, it's this go to that goes here. Reading into R1 plus 0x18. So basically there it does the decoding of the accounts. But let's assume we do not have an account and R2 in this case is actually 0. Then we go to here and we read into R2 another U8 pointer, R1 plus 0x8, which is, you know, the next byte, next 8 bytes, sorry. And if we know that this was 0, so then there are no accounts, then what's next is the 8 bytes unsigned number of instruction data. So what we're doing here is, this is so fun, I like it, disassembling my program. We're reading the number of instruction data bytes into R2. So R2 now has, how many bytes do we have for instruction data? Then, if R2 is bigger than 3, so 4 or more, so that's the check for the try into, you know, if you want to read it in the source, you know, that's basically comes from this. If we don't have 4 bytes, so 3 or less, then we got to do something with this unwrap or default. So should we also go, I mean, I can, you know, step through it because it's so fun. I could step through this with you. Yeah, let's try. Why not? So if we don't have enough bytes, like if we have 3 or fewer bytes, we go to 4 instructions further. So here. So we jump here. which also makes sense because the instruction above jumps somewhere else. Wait, no, hold on. If it's bigger, so if we have enough, we jump here. If we have 4 bytes or more. If not, then we set our R1 to 0x4 and our R3 to this, and then we call this. So this is probably and I'm guessing here, this is probably a call to a function. Let's see. Can I find out where this points to? Because we write something into the R1 and something into the R3, and then we call. So we set. I would like to know what we call. I mean, there must be a better way to disassemble this. When I call something, can you give me like more info of what I call? So it's not a go-to, it's a call. I'm calling another function. And all I have here, this is the one function entry point in my text. So I guess I'm calling something outside of the entry point. Maybe that's even already a syscall, but I don't think that this is a syscall. This is a syscall, probably. This could be the sol log. So anyway, let's just assume that here we call some other function that maybe prints the error message and errors. But yeah, whatever. Don't know exactly what that's doing. But let's assume that we have more than 4 bytes and we continue here, which is here. So then we write into R1 plus 10. So that's 16 actually. So we skip twice 8 bytes. First one being the number of accounts. Second one being the number of bytes for input, which is still in R2. And then we just step further for the R1. And then if R1, so what's there? The next, I guess, 32? Oh yeah, it's a 32 byte pointer. Already indicating that we read, 4 bytes from this address. Right, so we read from here. It's so fun. It can recycle R1 because it doesn't need that register later anymore. Because that's all. Because I was like, save the R1. Maybe we need that later. But no, we don't. That's why it overwrites it into R1. It could have written into R3 or whatever, but it's compiled efficiently. Anyway, so we overwrite R1, could be any other register. What is in R1 plus 16 bytes? So that's where the actual input data is. And it's a 32 byte pointer, so it takes 4 bytes only. It reads only the 4 bytes into the R1, and then it compares if this R1 now is 0x face. CEFA, that's where it's written, that's my number. If it's not that, go to somewhere else. And here we have it. I mean, this is kind of the solution already. This is my magic number. Spoilers. The 0x face is my 64K206. And if it's not that, then we go 4 further. So 1, 2, 3, 4. And then that's interesting. Look. Here it's doing the syscall. I think that's sol log. The 0x1 is sol log. The minus 0x1, the FFFFF syscall. And it might, I don't know how that works. Maybe it's put that there, but maybe it's always that. I don't know. But I'm pretty sure that that's the sol log syscall. And it writes into R2 0x15. So that's the length of the string. And it writes into R1 the pointer of where it should read from, start reading from. So start reading from this address and read for 16 plus 5, so 21 bytes, and write that into the sol log. 21 bytes is probably the length of this string. 1, 2, 3, 20, 21. Yep, there you go. That's the length of this string. And it points at 0x135D. And if we had when we dumped the contents of the read-only data, what are we looking for? 135D. 135D. So that's where we start. Nice. So we see that's in R1. That's because when you call the function, you basically set the registers again with the input data for that function. And the sol log syscall takes 2 arguments. 1, the pointer to the string, and 2, the length of the string to print. So into R1, we need to write the pointer, and into R2, we need to write the length. That's what we're doing here. We write the pointer and we write the length. And then we also see if that is the same. So if R1 is actually my magic number, then we don't go anywhere. We go to the next thing. And what's happening here is basically, first it's writing into R1 the 132A. So 132 and then 10 from here. 8, 9, 10. There we go. So it points here. So to this string, that's the one thing. Then it writes into R2 0x33. So probably 3 times 16 plus 3 characters is the length of this string, which would make sense because, 1, 2, 3 minus those 3 plus those 3. That's how you can calculate in hex. So yeah, that makes sense. So it's 1, 2, 3, 1, 2, 3. That's the length. That's how I... Smart. It's so cool. So that's the length of this string that it prints. So it did the same setup for the syscall, and then, oh, that's efficient. Then it jumps here. So it doesn't do another call from up here, but it just jumps to where it does the call from before as well. Oh, this is so cool. Oh, I enjoy this. Yeah, and then it does the sol log syscall. And then right afterwards, it writes 0 into the return register and calls exit. And that's the program. Ignoring all the account passing if we have accounts. There's just a bunch that we need to do if we actually have accounts that we need to parse. I think that's what's happening down here. Oh, and also, the stuff with if it's less than, there was another function. So there's a bunch of stuff that it does additionally. I still don't know where this goes. But also it's not so important, is it? Maybe in here, down here are also other functions that are not part of the entry point, but where I just couldn't disassemble them. Let's try and get that information in there. I can try and help you by putting more info into my SO file when I build it. Because this thing has 6.4 kilobytes now. I can put a little bit more info in there and then it might be easier. Let's look at that. Exact same program, but I'm gonna cargo build SPF with some flags. Let's set some Rust flags. Optimization level 0 and debug info 2. Let's do that. Okay. Now my SO file, oh wow, is 14.6 kilobytes. So obviously you don't want to do this when you build a program to production, unless you want to make it easy for people to debug your program. So now we added debug info. And this is something that you can't do for any program on chain, right? It's what the people deploying the programs would need to do. And I could, again deploy this. Now we will need more than 815. And if I now dump this to dump debug and then disassemble it, then now it calls it text plus. Oh, did I not? I wonder why it's now not saying entry point anymore, but oh, here's the entry point. The entry point is somewhere else now. Where does the entry point live? Entry point starts now the entry point starts here. And with that debug, though, it's actually harder to read because it's doing more things. And maybe it's also because I don't do optimizations and it just uses more registers and stuff, which again also makes it actually harder to read. This is indeed harder to read. So there are so many functions that it calls here. It calls this, it calls that. Do I even find my face in here? Yes. So that's even in the text, not even in the entry point. But look how much stuff is above that. So much stuff. Wow, yeah, that does make it harder to read. So what's the advantage of what I just did? Maybe it would be easier to decompile this. Oh, why did I call them SO files? Those are not SO files, those are S files. Not really, but basically it's TXT because it's output from the dump. But if I just had that, then it would be the S files. You get the idea. It's a lot more instructions and it's a lot less readable. You can also read the ELF file using read ELF. Read my dump. So if we read ELF, this is what we get. We have the header, magic, the class, the data, two's complement little endian, Linux BPF, entry point address 0x120. There we see it again. Section headers. Here we see the same thing, just, you know, different. Text starts at 120 and has this size. Relocation section. Oh! And here we see the sol log and the sol panic. Maybe it somehow maps those two somewhere, which I don't fully understand yet, but those definitely are the two syscalls that are being mapped somehow. Dynamic symbols contains 4 entries. One of them is entry point, and the other one sol log and sol panic. And for the debug, it's different here. Do we have any more stuff? We have a lot more raildin entries. We have them mapped several times. We also have sol mem copy. Yeah, okay. But that also doesn't, you know, give us much. Basically, I would still love to understand what is happening here, like what exactly it's calling here. What if I just do debug info and keep my optimization level? And then I do it directly on target, deploy, because why would I deploy and then dump it again? I have it here. Take this file. Here we just have the 600 instructions again. This is the simpler version, the optimized version. And yeah, for me, easier to read because less to, you know, think through. So there's something about the optimization that is actually pretty cool. It's back to 6.4. So really that other flag didn't give me anything, the debug info. Removing the optimizations in this case doesn't really give us much. But it's still easy enough if you just read that to get to where you want to go. I mean, admittedly, it's also a very simple program. It doesn't do much. Like if it gets more complicated, then you will be lost with your ASM. Because it just, you know, once we get to the point where there's like so many things where you're like, what the hell is happening here? We might need to decompile this to get an idea what's happening. But that I leave for the topic for another video. Possibly the next one, we will see. Now, if you excuse me, I'm gonna still change that program a bit, such that you have something to disassemble and look into. Oh, by the way, what I want you to do then, obviously, is to call the program. Maybe let's also do that. That's my program, hack me, and then I call the program with 0 addresses and data, new uint8 array, and we know what data we need. CE, FA, 0, 0, because 4 bytes at least, otherwise. So that's in little endian, FA, CE, face this. And yes, I could do get U32 decoder, the other way around, encoder, encode 0x face. Same. And then I just simulate and send this. If I wouldn't want other people to be able to know what I did, then I don't send it, obviously. Simulation is just fine in this case because I don't want any extra state change. I just want to see if I get to that message. And there we go. Oh no, I got hacked. We made it. We nailed this. And if we had anything else than face, then obviously we don't get that message. So yeah. And if I want the people to know what I'm doing, then bam, I can also send that transaction so people can, you know, look at it here and then see what I put in as instruction data. CIFA. Cool. But if you excuse me, I'm gonna change that program a bit. I'm gonna leave those messages the same, but I'm gonna change that number and maybe something else, such that it's not too easy for you. And then I'm gonna redeploy and let you do the challenge, disassembling this program and trying to call it to get here. All right, I hope this challenge speaks to you and you're like, oh, I want to try this now, or you already did and you managed. Congratulations in that case. While I have my hands up here, did you see those YouTube videos? There's more stuff that you can watch, and you can also subscribe if you haven't done that yet. Give it a like if you enjoy the challenge, and then I will see you in the next video. And let me know if you want more challenges, because I might have a few more ideas.